All right, in this video, we're going to see how we can use the Jacobian and the eigenvalues of the Jacobian to determine the stability of the fixed points for a nonlinear system. And we're going to be looking at this epidemic model that we studied in a previous video. And on the left side of the screen here, you'll notice there's the old equation that we derived and the two fixed points that we found by setting Si and R equal to S star on both sides of the equation and solving. And we obtained, again, two fixed points, one that was the disease-free state where nobody was sick, and the other was what's called the endemic state where there's some fraction of the population that is infected indefinitely. All right, and what I would like to do is look at whether those fixed points are actually stable, and we're going to use the Jacobian for that. And so to start off, on the right, I've actually wrote up a script in Octave to compute the fixed points using the parameters that are given here. So I've defined n, beta, r, and gamma as specified on the left, and the fixed points are can now be calculated using those values. And so the reason I like to do this this way is that if I want to change one of the parameters, I can easily recompute the fixed points just by rerunning this script. All right, and the change term from the equation is written here as a function, and so let's quickly check to see if the change is indeed 0 at those fixed points, meaning that if you start at one of those fixed points, you will stay there. And so I'll just run that selection here. If you go to the window, there we go. It says the change for the first fixed point is 0, and the change for the second fixed point, which I should probably name correctly, was also 0. All right, so that means they are indeed fixed points. If the change is 0, you stay there. But what it doesn't tell us of whether they're stable. And for that, we're going to need to compute the Jacobian matrix. And if you recall, the Jacobian matrix involves taking all of the derivatives of the individual components. So we've got three components here: the change in S plus S, the change in I plus I, and the change in R plus R. And there should be subscripts on the right-hand side here. So that should be Sn, In, Nn, Rn, and so on, since those are at time n. All right, that looks a little better. Okay, so there we go. So that's the equation that we want to take a derivative of. And so we're going to take the derivative of the first row with respect to S, then I, then R, and then the same for the second and the third rows as well. All right, so if you look at this first row and you take a derivative with respect to S, notice from the first vector we will get a 1. And then from the second term we have a beta S times I over n. If I take a derivative with respect to S, we'll have beta times I over n. All right, now we need to take a derivative of that same first row with respect to I. And there's only one term with I, and it's that negative beta Si over n. So its derivative would be negative beta times S over n. And then lastly, we'll take a derivative with respect to R, and that's just going to be gamma, which I'm calling G in Octave. All right. And we'll move on to the next row. Taking a derivative with respect to S, I see one term, the one in the middle here, and that is going to be derivative beta I over n. All right, the next one, taking derivative with respect to I, this one's going to take more work. Notice we have a 1 from the vector, the old value, plus, when we take the derivative of the next term, that has an I as well. And so we'll have a beta times S over n. And then we'll have minus R from this last term. And then if we take a derivative with respect to capital R, notice it does not appear in that equation, and so the derivative will be 0. And here I'm using just the dot, dot, dot to continue on the next line, so it makes it easier to see that this is indeed a matrix. All right, one more equation. Derivative of the last row with respect to S is 0. Derivative with respect to I is just going to be R. And then derivative with respect to capital R is going to be 1 minus gamma. And so there we go. We've got our Jacobian matrix, and I've created this as a function so that given a value of Si and R, I can actually get the numbers that correspond to each entry in the matrix. And I will run this whole thing now, and you'll see that the Jacobian matrices are displayed, and when you compute the eigenvalues, we will have the following. The eigenvalues for the first fixed point are 1.975 and 1.4. All right. So for n0, 0, we have lambda 1 is 1, lambda 2 is 0.975, and lambda 3 is equal to 1.4. And the key thing to notice there is one of the eigenvalues is positive, and so this must be unstable. Not that it's positive, excuse me. It's greater than 1. And if the absolute value is greater than 1, we said that means that we have an unstable fixed point. So what does that mean? That means that if the system starts exactly at the disease-free state, then, well, of course, you will stay there, right? If there's no infected people, you can't get sick. But if you start with just one infected person, you start slightly off of that disease-free state because it's unstable, the system is going to move away from the fixed points, and what you'll have is an outbreak. Okay? So for the second term, the second fixed point, I won't even bother to write out the formula since it's a little messy, but that's the endemic state. That is, the eigenvalues were, it looks like they are complex. And so we have lambda 1 equals 0.95 plus or minus 0.085 I. So actually that's lambda 1 and 2. And then the last one is lambda 3 equals 1. And you can take absolute values of complex numbers. Absolute value of a complex number, if you have the number a plus ib, where a is the real part and b is the imaginary part, the absolute value is just the square root of the squares of the two parts. So I'll take the absolute value of that first eigenvalue. That would be the square root of 0.9475 squared plus 0.08511 squared. And its absolute value is around 0.95. And if you plugged in the negative 0.085, you'll get exactly the same thing since it's squared. And so both of those have absolute values around 0.95. The other value is 1, which means this one is right on the edge. And that's where a case where it's not clear whether it's going to be stable in all cases. And the reason for that is there's some non-uniqueness here. If you were to say add a certain number of people to all three categories, you add a few susceptibles, a few infecteds, and a few recovereds, and keep the ratio of susceptibles to infecteds to recovereds in the population fixed, then you would see that that would not return back to the original state. You're essentially getting a new fixed point. And so this is a result of the fact that the system here depends on the population size, right? All of the fixed points depends on n. But other than that, you see that all the other eigenvalues are indeed less than 1. And so this is what we would call a neutrally stable fixed point. But for all practical purposes, keeping the population fixed, it will behave as a stable one. All right, and we can check that with a numerical simulation. So let me switch gears here for a minute. I'm going to go to a little more involved calculation. And so let's set beta is going to be equal to, we said we want it to be 1/2. We want L to be equal to, or gamma to be equal to 1/40, and I was using L here, so it's the same thing. R is going to be equal to 1/10, and the population size we said was 1,000. And all right, so we'll run this simulation, see what happens. Okay, and notice, even though we started with just a few infected people, the red curve was really small. As time went on, the red curve leveled off, and it's precisely at the value of the fixed point that we calculated before, which I believe, if we scroll back up here, when we originally did it, what do we have? We had 160 for infected, 200 for susceptibles, and 640 for recovereds, and that's exactly what it seems like they're asymptoting to in this case. And the nice thing about understanding the fixed points is we can then predict how the long-term behavior is going to change, and we can do so without having to run a simulation because we actually have a formula for the fixed points in terms of all of the parameters. And so, for example, notice this first fixed point. We can see that if we increase the value of R, the rate at which people recover, that means there will be more susceptible people in the long run, since the value of the fixed point is proportional to R. Whereas if we increase beta, which determines how often susceptible and infected people interact, then you'll see that there will be less susceptible people in the long run. So by being able to write down a formula for the fixed point, we can not only determine where the system ends up, but we can determine what factors will affect where you end up. All right, so this sort of analysis, finding fixed points and classifying their stability, is a very, very powerful tool. It can complement your numerical simulations because it tells you not just what the answer is, but why, and it allows you to better understand how the individual components of the model play off of each other to affect the long-term behavior.